Perfect. So I think Stefan already introduced me. I'm the Chief Architect for Standards, Consortia, and Industrial IoT at Microsoft. Been in this role for several years, been with Microsoft for 20 years, and I represent Microsoft in many different consortia, mainly OPC Foundation and other manufacturing or industrial IoT related consortia. So like I mentioned, about 7-8 years ago, when we defined the Azure Industrial IoT platform, we decided to go all in on openness. And we created 4 pillars to that strategy, and to this day it's been our differentiating quality. Part of that obviously is the open source contributions we made to the OPC Foundation, to Digital Twin Consortium, other consortia, and also building an open platform based on modular components, so people can pick and choose the ones that they really need and only pay for their use. Heavily, obviously support open standards, OPC UA being the key, cornerstone of that open standards strategy. On the edge and in the cloud, most folks just use OPC UA on the edge for last mile connectivity to the asset. We use OPC UA as similar to what Procter & Gamble actually talked about in the previous talk. As a, obviously also for connectivity, but mainly for normalizing the data on the edge, close to the machines, also similar to what Reno was talking about. That has been the winning strategy. And then also sending the rich OPC UA metadata to the cloud, maintaining it there, as well as obviously telemetry time series data for our analytics in OPC UA PubSub format. So again, a completely standardized telemetry pipeline and data model on the edge and in the cloud. So the data model is actually one of the most important parts of OPC UA, quite frankly. Obviously a best-in-class security, and this has great interoperability and all the other stuff that are important, but the data modeling is the key benefit in my opinion. So again, we've been with the OPC Foundation since 1996. We started integrating OPC UA into Windows IoT back in 2014, I think it was, and then started the journey with Azure IoT in 2016. And to this day, I think, I haven't counted in a while, but we're well over 5 million source lines of code that we contributed to the OPC Foundation. So the OPC UA technology is very complete. It has very different use cases, right? So it's kind of the Swiss Army knife for industrial interoperability. But what folks also really need to understand is that with the standardized information models, you're also standardizing the schema, the semantics of the different machine types. And that's where it really starts paying dividends, because you can decouple the connectivity and browsing. I mean, obviously OPC UA is discovery, so in theory, what and what a lot of people have done in the past is when they do an industrial IoT project, they go to the site, they connect to the machines, they convert them to OPC UA, then they do a discovery process to discover all the data models and all the tags available, and then they start sending data to the cloud. And after that, they start building their cloud infrastructure. But with the semantic standardized data models, you can do that completely decoupled. So you can create your analytics cloud. It's usually done by the IT crowd, right? The IT folks within a manufacturer. And then onboard factories later done by the local on-premises OT crowd. And the connecting tissue between those two organizations is OPC UA, right? And you can do that independently, and that's, I think, one of the big advantages that a lot of people underestimate. And that's why my suggestion to obviously the machine builders, but also to the end users, the manufacturers, is you need to adopt these standardized information models. The VDMA has over 600 companies involved in building these. And manufacturers, end users actually need to ask for them, right? If you don't ask for it, you're not going to get it. So don't just put OPC UA in your requirement specification, but put in what information models, what standardized information models you expect, and then you will get them, and then the adoption will accelerate significantly. So what happens if you don't have OPC UA built into everything? I think Renault already mentioned it. Procter & Gamble have the same strategy. Well, you need to, buy industrial connectivity software and convert your legacy interfaces, your legacy data models to OPC UA. Now, that's a really tedious job, right? And, it has to be done. You need to have that consistent standardized data model. But it's a one-time job, right? Once you've done it for your site, you don't have to do it again. So what Microsoft has done is we've created the largest ecosystem of this industrial connectivity software. We convinced these partners offering these industrial connectivity products to bring them onto our Edge platform. So we put them up on the Azure Marketplace. They're available for everybody to see, and they just work. And you can deploy them through the Azure portal directly, so they're fully integrated. And I think that's a reasonable strategy. So obviously, what does this mean to an average, industrial IoT project? Well, now, warning about the slide. These are estimated numbers, so don't get wrapped around the axle of the actual percentage figures, right? But the relativity of them one to one another, right? So, on a worldwide basis, across discrete manufacturing, process manufacturing, and the energy sector, okay, I believe that roughly 10% of the assets that you want to connect for your industrial IoT use case are discoverable. And then the kind of split between OPC UA enabled assets, usually PLCs, and non-OPC UA enabled assets, usually PLCs, is about 40-60%. So from the 10%, about 4% globally are OPC UA enabled today. 6% globally would be discoverable, but through some proprietary interface. Now, obviously, if they're OPC UA enabled, you don't need any industrial connectivity software. You can just connect it to, an industrial edge platform like Azure offers, with full OPC UA support built in. But again, that's 10%. So I think roughly around 90% are not discoverable. So, they just sit there. They have some sort of interface that doesn't support discoverability, and you just need to have a data sheet with all the tags defined in it, and then manually type it into your industrial connectivity software. Around 63% worldwide, I belive, are fixed function assets. Think of energy meters, pumps, valves, temperature sensors, whatever it may be. But the data model in those assets never changes. It's in some PDF that the supplier gives you. And again, you just need to get the PDF, type in all the tags into your industrial connectivity software, and onboard that particular asset, right? Roughly around 27% of those assets are actual PLCs, so they've been programmed at some stage, and there really isn't, a manual from the vendor that will tell you what the data model looks like. You really have to find the person who programmed the PLC, if they're still alive and they're still working for you, right? And then obviously get them to tell you how a particular data model looks like. And it's usually in some Excel spreadsheet, and you just have to type it in again manually into your industrial connectivity software. Now, there's not much we can do about the programmable PLCs that are not discoverable. There's just a pain, but it needs to be done. So what we can do is try to automate the 63% case worldwide. So the non-discoverable fixed function assets. And we can try to use things like ChatGPT to generate the data model to allow the onboarding of the asset automatically. Okay, so that's what we did. Together with Siemens, we looked at a schema that we could use to define those assets. And very quickly, we came across a W3C standard called WoT Things. It has a JSON-based thing description that you can use to define the interface of an asset and its tags in a very compact JSON-based format. You probably saw the presentation yesterday from Siemens on WoT Things. So we're a big fan because it is so compact and it's so, complete in terms of being able to define an interface. So here's an example from a Siemens energy meter. It's a Centron PAC 4200. And as you can see here, it's relatively simple in its layout. Obviously, it's human readable. And most importantly, large language models like ChatGPT can generate such a thing automatically, if done right. So what does a typical architecture for this look like? We actually went ahead and already built a proof of concept for this and contributed that to the OPC Foundation. So if you go to the OPC Foundation GitHub repo, you'll see a thing called UA Edge Translator, and it's a reference implementation of such an industrial connectivity software. And the key new component that it has is a control interface to configure the software for a particular asset, to onboard that asset to the industrial connectivity software. And that control interface is based on, yes, you guessed it, OPC UA. So the idea is that we want to make it as simple as possible for industrial connectivity providers to implement this, right? And they all already have an OPC UA server built into their industrial connectivity software. So it was obvious to say, listen, all you got to do is to define a bunch of methods in your OPC UA server to implement this interface. So we decided that we want to standardize that interface through an OPC UA companion spec. We created the work group for it. The kickoff is next Tuesday, okay? So if you're interested, send me a mail and I can send you the invitation to the kickoff meeting. It's a super simple interface, right? I mean, right now it has 3 methods: configure asset, get number of configured, or get configured assets, and delete asset, right? So I don't think it gets much simpler than that. Of course, it's probably, by the time we're done, we're probably going to have a few extra helper methods to make it more complete and user-friendly. But, as at a minimum, those 3 methods need to be implemented. And again, UA Cloud Translator already does that, so you can see how simple it is. And of course, configure asset, that configure asset method takes an input parameter, which is the WoT Things thing description, okay? So simplified, obviously, Azure OpenAI as a ChatGPT enabled service generates the thing description automatically, sends it to some sort of user interface. In this case, the user interface was built into UA Cloud Publisher, which is again an open source project I'm developing, but it's based on an OPC UA PubSub publishing tool, which has an OPC UA client interface, southbound, and an OPC UA PubSub interface using MQTT or Kafka northbound. And then as UI, that was the obvious choice to put the UI into. So obviously you need to provide some sort of prompt for the user that they can say what exactly the asset is that they try to onboard. And so the UA Cloud Publisher has that user experience in it. I published a blog post on this on LinkedIn, and at the time, it was my most successful post ever. I had over 30,000 impressions in 3 days, so that was pretty good. So obviously, people are interested in this. So what does it look like? So here's a screenshot of the UA Cloud Publisher user interface, and again, it's super simple. You get a chat prompt where you basically type in the name of the asset that you're trying to onboard. And then there's a generate and download file button. So you click that, it goes off, contacts the Azure OpenAI service with, the prompt that the user provided. We are doing some extra prompt engineering. I'll have more details on that later. And then you get, the file gets downloaded automatically into your downloads folder on your PC. And then, of course, you're not done, right? So then so here is, before I go into the next step, here is what that file will look like, more or less, right? So again, we don't claim perfection, but it's a lot better than typing in all the information by hand, right, from a PDF. So this is what this energy meter looks like. It has a Modbus interface. So, and to the right, you see the generated thing description in JSON format. And as you can see here, there's two things I'd like to highlight. So first of all, you can already add the information of how you want to map this particular Modbus device to OPC UA. So in this case, since it's an energy meter, we want to map it to the standardized OPC UA companion spec for power management energy measurement. So that's Profinet energy measurement, PNEM, right? And it's a companion spec released a while ago. I know that the VDMA is also working on a more generic energy measurement specification. I think it might end up in UA for machinery. I'm not 100% on that, but anyway, they're working on it. And then once you define the tags, you can already specify the OPC UA type that you want to map a particular Modbus register to. So you end up not just with a mapping to OPC UA, but a mapping to a companion spec, standardizing the interface. So then, like I say, you get this file downloaded to your PC, and then it's your turn to basically validate what was generated automatically. So you can use online thing description editors for this task. Siemens contributed this editor to the Eclipse Foundation. So you could just go to the eclipse.github.io/editor and it pops up. So it's hosted as a web app by the Eclipse Foundation. And it does a few important things. So first of all, it validates JSON, and it also validates the JSON schema or the Web of Things JSON schema against the file that you put in. And then, of course, you can start modifying the file, make sure that it's complete, make sure that everything that you expect is in there. And then you save the file again. And then as a next step, you basically load the file into your UI. So this is done again in the UA Cloud Publisher UI. So you can pick the file and then basically type in the endpoint, the IP address of UA Edge Translator, or if you're using a commercial system, which eventually will be available as an industrial connectivity solution which supports this interface, you just basically type in the endpoint, send the file to the connectivity solution, and it onboards the asset. It's as simple as that. So in the case of UA Edge Translator, here's the standard OPC UA reference client that Microsoft contributed to the OPC Foundation. So you can just connect to the UA Edge Translator. Obviously, there's an OPC UA server built in, and You know, here, this particular Siemens energy meter is onboarded already. So you can see it, and you have all the different tags defined in it. In the middle here, I probably should have expanded that before I took the screenshot, is the asset management interface that, you know, we're proposing and we're going to define in that working group. So this is the one that has, you know, configure asset, get configured assets, and delete asset in it. And that's it. And then you can obviously connect to the industry connectivity software like you would normally. One important part that some connectivity solutions already do, like, you know, I know Softing Datafeed does it, is it would really help if your mapped assets in the industrial connectivity software end up in separate namespaces. So you have one namespace, OPC UA namespace, in the OPC UA server's address space per configured asset, right? Because otherwise, I've seen implementations where you just get a flat list and all assets, depending on, you know, doesn't matter where they come from, end up in that flat list. And then once you start connecting to it and trying to figure out which asset belongs to what, or which OPC UA telemetry tag belongs to which asset, it's a real pain. So it's better to put them into separate namespaces. Okay, so now, how do we do it, right? And the key to success turned out to be two things. You need to use ChatGPT 4, so 3.5 is not powerful enough to generate a complete Web of Things thing description, but GPT-4 is. And then you need to do some training and some prompt engineering, right? So training the default GPT-4 model can be done, for example, in the Azure AI Studio. So first of all, you can tell the model what it is and what you expect back. So you don't get random, you know, descriptions about what Web of Things is, for example. So you can tell it that you just expect Web of Things thing descriptions back. And then you can give a few examples, like what the prompt would be and what the expected result would be. And that obviously has a huge impact on what it generates. But don't get me wrong, it can generate other things apart from what you give as examples, right? And that's the whole point of using AI, that it can infer from your examples what other things you want to provide. And then on the parameter side, you need to basically, in this case, you want a specific answer. You don't want, you know, the large language model to be creative and come up with some goofy stuff. You want specific answers, so you need to set the temperature really low. It's one of the settings in the parameters of the large language model. So you want to be, I think in Bing it's called more specific versus more creative or something like that. So you want to be specific. You want Web of Things thing descriptions coming back. And then, of course, I want to show you a real demo, right? So what I've done is I've set this up exactly like in the example I just showed you. So I made sure that, you know, it knows that it's a Web of Things thing description generator, and I gave it one example and one example only. And then for giggles, I said, okay, I happen to have a PV system on my roof, right? And the converter converting the PV DC current into AC current so I can use it in my home is from Fronius. It's a Fronius Sumo. And I said, okay, generate a Web of Things thing description for Fronius Sumo, and that's what it generated. And I went, okay, so this looks like the REST API that the Fronius Sumo has. And I said, well, I'm not interested in REST. I want Modbus. So I said, okay, try that again. So generate Web of Things thing description from Fronius Sumo using Modbus. And sure enough, it creates Modbus for me, right? So here it's exactly the same as I gave as an example. So this is the Modbus schema for Web of Things. So you have, I think this is the unit ID of the Modbus device. Then you have the register address. Quantity is the amount of 16-bit Modbus registers that you're supposed to read. This, of course, is a float. What else is there? There's the name of it, so it's current power generated by the inverter. It gives you the polling time. It's a holding register, and so on. And it even gives you the unit, so it's watts, right? So it just works. Although I didn't train it on Fronio Sumo, I only gave it one example for Siemens Centron Pack. So it really works, and it really means that no matter what you put in, you will get a good example, right? So I think this is a real help. And again, it's a good example of where these large language models can help. It basically removes a mundane job that you would have to do by hand yourself in these industrial IoT projects if you didn't have this tool. And so you can focus on more important work and spend your time on more important stuff, right? So let's go back to the presentation. You need to switch again. Okay, so that is the demo. So what's next, right? So obviously we want to build a custom large language model just for Web of Things thing descriptions, right? So we're working on that with our OpenAI experts together with Siemens. And obviously we already have access to the this type of GPT-4 base model. So that was a big help. But ideally, we also want to train this model with more than one thing description. So hundreds are great, thousands are better. So you really want to get as many examples fed into the model such that it can do a better job of giving you the results. And then, of course, we want to deploy that model on or in Azure OpenAI service. It has a REST interface, so integration is super simple. And then you integrate that into your existing products, right? And that's fundamentally what we're working on right now. So just because we talked about, a specific case, what would a full model or what would a full product where this could be used look like? So obviously, we've done a lot of work with the OPC Foundation and the Digital Twin Consortium. Here is the reference architecture of what we believe a complete industrial IoT reference architecture should look like. Obviously, there's lots of OPC UA in it, but we also integrated the Asset Admin Shell, for example. The Asset Admin Shell is a great interoperability tool for distributing data along the supply chain. It shouldn't be installed on the shop floor, but it's good for the supply chain. And we're creating things like product carbon footprint with it. But we've integrated pretty much, the way this worked is, we made an initial contribution to the Digital Twin Consortium just for ontologies for the Azure Digital Twin service, but then people kept asking for more integration. We added a bunch of stuff and we keep adding. So, we're going to keep this up to date, keep this relevant. And we add the services that people want to use. And with that, I thank you for your time, and I wish us all peace in Europe.